Right, good morning. Today's speaker is Pantelis Eleftheriou, and he will tell us about decomposing groups, correct?
Yes, thank you, Patrick. And thank you for having me speaking to you. Also, many thanks for having me in the program. It's really very nice to be here. So, before I start decomposing groups, let me make two self-advertisements at Leeds. There are going to be two things happening. One is a 3-week program in model theory, July 18 to August 5. These are 2 weeks summer schools and a 1-week workshop on the occasion of 60th birthday of Kobe and Sergey. And well, if you are early career or students, then you get some good discounts for attending them. You need to apply for participation in the summer schools. The deadline is April 1st, but it's straightforward to apply. And you need to register for the workshop by April 15. All the information is online. This has been announced on ModNet. And the second thing is there is going to be a 3-year postdoc position in model theory. This has not been announced. It will be announced within a month, hopefully. And well, if you think you may be applying, then you can already talk to me and discuss about it. Okay, so that's about Leeds and how decomposing definable groups. So this talk is about definable groups in various contexts, staying within or going beyond minimal setting. And this is really going to be somewhat a survey talk, stating some open questions, reporting on their progress, and some examples, essentially no proofs. Okay, so now the general question, the most way I could state a question that captures the flavor of this project is the following. General question. And it will be actually a little too vague to even be called a question, but here it is. Given structure M, which is made up of two structures, X1 and X2. Can we decompose groups definable in M into parts coming from X1 and X2 into groups or sets definable or internal, as we will want them again, in general coming from X1 and X2. So it's indeed very vague because there are three expressions in quotation marks, and the goal of this talk is to give precise meaning in some ways to these expressions. In particular, we will give two interpretations of made up of. Okay. So let's start with that. Let's start explaining the made up of. So two contexts. One is where we just put the two structures together, imposing no interaction between them. That's the disjoint union. And M is the disjoint union of X1 and X2, which probably you know is the two-sorted structure where we have as basic sets the definable sets here and the definable sets here. Or I think it's a low form of generality. Just write this as the structure whose universe is the disjoint union of the universes, and again we take all definable sets, next to basic sets. So there is no interaction between the two structures definable here, meaning that there is no definable injective map between infinite sets. Infinite sets. Next one. Next. And this is actually a corollary of the general description of definable sets that you get almost by definition, that definable sets here in this end are finite union of boxes. Finite union. Sets finite union of sets here or products of sets here and here. Of sets fx1, fx2, and
Cartesian products.
And Cartesian products.
Let's say Cartesian products because trivial set is also
x to the 0.
Yeah,
sure. And S1 process 2, where Si is F I. And this is after permuting coordinates. Because I could have x1 cross x2 cross x1. After. Okay, so this is a very nice description of definable sets here, and we can ask, how do definable groups look like in M? Are they, for example, direct products of definable groups in the two structures? So we will get to that after we also look at the second context, okay, which is perhaps more in line with the tame phenomena over the reals. This presented these weeks here. And so here, okay, so here we have no interaction between the two structures, and now we will put them together with some interaction. And the easiest way to impose interaction is to let the universe of one be a subset of the universe of the other. So now, just because it's more traditional, I will denote by R x1 and by P x2, okay, where the universe of P is contained in the universe of R. So then every definable set here lives in a power of R, so this makes sense. Okay, and well, depending on what P is, this may be tame or not. Whereas here, if x1 and x2 are tame, then the disjoint union is tame as well. And there are two ways to construct such pairs. The one is where the P, the universe of the structure P, is already not definable. The other is where it is definable. So first way is where P is definable in R. And in this case, already having just the universe of P, we have a new structure. This is a proper expansion of R. If I wanted to see it this way, then we could write RP. This is the structure we're interested in, and this is R with structure P, where the structure P is the U structure on P. So we impose no more sets than just P. Okay. So this is the P where universe P, and then we have all intersections with R definable sets. are definable. Are definable means definable.
And when you say definable, you mean with parameters?
Yes. So yeah, everywhere definable is definable. Okay, so now examples where we get a tame pair. Well, we have seen. So if P is, but these are more what I would be interested in. P could be, okay, R is the real field and P is the real closure of Q, or 2 to the Q, or a density dependent set. Is really dependent, or 2 to the Z. Some examples. In this case, M is tame, and let's call this like M. This M is a tame pair. Okay. So tame is can have many more examples, but for this talk, let's just fix some examples. Okay, and if you had P is completely, you had P the integers, then it's not tame as field and fish focus.
So just to be clear, these are not examples of
Sorry?
whose examples of R and P are not examples of. Those are not
P.
where P is not definable. Okay.
Sorry, here I'm talking about not defined. Sorry.
Oh, okay.
Sorry. The first I want to be there. No, defined. Thank you. Okay, so obviously, if okay, maybe I didn't give any examples here, but well, here any structures you take with joint union, well, it's an example. But I still maybe it's worth mentioning that examples that will appear in this talk is, for example, R ordered class with itself. It's already interesting to ask what are the final groups here. And another natural example sometimes in procedure is if you have a nominal structure and you take Z class. The reason why this appears is because when you look at definable groups in nominal structures, their universal cover is not definable in the nominal structure. It's V-definable, but it turns out to be definable in such a disjoint union. Okay, we will not really speak about universal covers or that result, but these are the natural examples that we are concerned with. And here, obviously, if I put Z in a disjoint union, then you remain tame, but here you impose this interaction and you're no longer tame. Okay, so what's the interaction we impose? We impose that there is an injective map from P, from sets in P to sets in R, the inclusion. Right? And in these examples, actually, you don't have the opposite direction. So you don't have injective maps from R to P. Right? Okay, and the second, so I will say more about descriptions of definable sets comparing to this in a moment, but let me say the second case where I could have P definable in R. Well, I don't know, there may be many examples that have not been studied, but the one that I have worked on is actually so that the pair stays within the minimal setting. And that's when you start with R being the real ordered group, and you put as P, as a structure P, just having the restricted multiplication. So e.g. And P 0, 1 1 square. So here M is just real order group with restricted multiplication. And we know from theorems that there is a marker delay, but this lies strictly between the real order group and the real order field. And it's called semi-bound. So let me call this a semi-bounded pair. And again, semi-bounded pair can mean something more general. It could mean really any minimal expansion of an order divisible abelian group with bounded sets, okay? As long as it stays on minimum. And what I said, it's called semi-bounded. But for the purposes of this talk, we can think of a semi-bounded pair as that. Okay. So, and now here we have the definable sets, unions of boxes. Right? What about definable sets here, where they are finite unions of cones? And I would say just a bit about it. Okay, so go right here. The definable sets in 2 are finite unions of cones, which, depending on which context you are, it may be harder to define or easier. Okay. So roughly speaking, a cone roughly is a set of the form H S cross J. Okay, and now I want to explain what S cross J is. It's not going to be as simple as S being definable in P and J being definable in R. Okay, but what is it? So let me say we really want to understand definable sets here in these structures in terms of definable sets here and definable sets here. So, for example, in the semi-bounded structure, you may say that, well, this is a reduct of the real field, so we know a cell decomposition coming from the real field that tells us something nice about definable sets, but it doesn't tell us much about how those sets depend on this structure and depend on this additional information. So I need a word to define what it means to be coming or relating to this additional information, and that will be being internal to it. So let me just explain where it's coming from. And this is very general. If I'm saying structure, X is a collection of definable sets, and Y is a definable set. And Y is X internal. If there is an X in this class, and there is a definable of F, such that F of X to some power, that is N2, contains Y. I have not specified the arity and the domain of F, but it's so that this makes sense and it's true. And now, for tame pairs and semi-bounded pairs, we preserve a terminology for things that are p-internal. And semi-bounded pairs, we call them small. Small means p-internal, if I view P as the collection of definable sets in the structure P, and lots otherwise. Okay. So, for example, the unit circle is internal to this this P. Okay, good. All right. And now these are what I will put for S and J. There. So let's come back. Definable sets are finite unions not of boxes, but of this kind of products. S is a small set, J is a large set. And here is where roughly is concerned. You can say much more about what J is. It's actually almost like a product of co-small sets in intervals. And that's even not true, but anyway. This is actually true, but it doesn't give us much information as we could have. And H is a transformational box. Okay? It's an R-definable map. Again, I don't specify the domain of it, but so that it contains, of course, the S cross J. All right, so let me give you a picture about a cone in the semi-bounded case. In the semi-bounded, we could, for example, take now 3. We could take a graph of a multiplication, the resistive multiplication in one of the planes, okay? And we could stretch it unboundedly much and semi-linearly in this direction. So we could have this kind of system. Okay. So if this is S, which is internal, and J is the this half axis, then this object is S. So we use just H to be the addition map. Okay, and the cone decomposition says that every definable set here is a finite union of such objects. And what is interesting is that the same spirit, the same kind of structure theorem is true in all these pairs. That makes me wonder where else this structure theorem is true. And I think it's, well, I have several contexts in mind that it could go through. For example, if you replace all minimal structure by a geometric structure, you have lovely pairs of geometric structures. These are objects that were studied by Bernstein, Vasiliev, among others, but and tameness have been shown, but not as a description of definable sets like this. Or more in the neo-stability spirit, you could have this being a distal structure and this a NIP pair, and you could ask about such a decomposition. Or finally, you could have this to be a distal structure and this a DP minimal structure, and you can ask about such a decomposition. I'm mentioning the last one because here, as I said, we could have something more refined, and somehow through these cones we get a notion of dimension that captures how large your set is, the same way that the notion of dimension in O-minimality captures how infinite you are. Okay. And here, if you had a distal expansion of a DP minimal structure, you can talk about DP rank. So I'm wondering if the notion of dimension you could get from such a structure theorem there could correspond to the DP rank. Okay. Good. What about sets? It's good to know some decomposition theorems about definable sets if we want to do decomposition for definable groups. And maybe this decomposition program is not so present in a tail expansions program. Actually, I remember Philip once telling me that once he proved that the structure is tame, he no longer works on it. But here, my perspective is that I take a tame structure, I know something about model probability, something about definable sets, some open core, and I'm trying to find the decomposition of definable sets, get more description, geometric description from that start point. All right, and my motivation has been to apply this decomposition in order to understand definable groups. So let's move to decomposing groups. Okay, so let's fix actually M S in 1 or 2. And G a definable group. Okay. So what can we say about groups definable in these objects? As I announced before, the first question to ask is G a direct product? Most of the times when I write equality, it's up to definable isomer. It means definable isomer of groups which are xi internal. Okay. So in the second case, x1 will denote R and x2 denotes P. Right? And this question is no. In almost all examples. The reason why it's not in all examples is the idea is about the same. And I want to illustrate that idea in the case of this joint union. Okay. So take M being the joint union x1, x2, where xi is a copy of the real ordered group. I have two copies of the real ordered group, and I take that there is joint union. So, of course, direct products are definable in this structure. So we could take, let's call X plus. We do overuse of the symbol plus in this example. Is the direct product of say X 1 plus. That's for sure definable. And now we could actually take quotients of these groups by some lattice and take those, the product of those. Let's let G1, GI be 0, 1 plus modulo Z. So we add two things as usual if the usual sum is here, and we subtract one otherwise. This is definable in xi. And their product is again definable. 1 cross G2 is definable. And to construct an example which is not product, I'm going to rewrite this in a little more fancy way and tweak a bit the definition, get something that a group that hides the definable, the one-dimensional definable subgroups. So this is 0, 1 times 0, 1 with plus modulo the lattice that is generated by 0, 1 and 1, 0. Okay. I mean, this is really isomorphic to R squared over Z squared. But I wrote it this way because now I can change a little the definition, right? So maybe we have picture here. Right, so we took this group, okay, and we took R square plus, and we modeled out the lattice generated by these two elements, and we could change a bit the lattice and put the lattice generator somewhere here for A irrational. The other lattice is there. So the same before. On A, where A is not in Q. And I claim that this is not a product.
Shouldn't the second factor be 0, comma A instead of 0, comma 1 or D?
0, 1. This is the first.
Yes, and the second one, you wrote 0, comma 1 cross 0, comma 1 again,
Right.
but shouldn't that be 0, comma A?
Here.
Yeah.
No, I wanted 0, 1. Yes. I mean, that, if you do a fundamental domain here, and you cut it and patch it, you get this as a fundamental domain. This is fundamental domain for this group. I don't want it to go up to here. I mean,
how is it?
but there is no reason to, I mean,
So how do you add in this group 0, 1 cross 0, 1? You add
let's add this to itself.
so okay, if you have an element high up in this square, a little bit above this point 1, comma A, how I don't understand how the definition, how this group is defined.
I add two pairs as usual. If their usual sum stays in the box,
Yeah.
and if not, then I send it to that element of the box that differs from the usual sum by an element in the lattice. So if I wanted to add this to itself, I would normally go here, but this is not in my domain. So I have to send it. The sum of this to itself is that element in the box that differs by an element in the lattice, and that element is this point here, because this vector is a vector in the lattice.
1, 0, 1, and 1. So what letters do you have in mind here?
Maybe another picture. So one vector is here, another vector is here, right? So this is the usual fundamental domain. Right? And now this is the same as taking this part and moving it here. So I'm just changing the fundamental domain by cutting some pieces or translating them by adding the
Okay.
line.
Yeah, I guess okay, good.
All right. Okay, So this is not a product of xi internal groups. And I will argue about this orally. Well, if it were, then there should be one of the two xi internal groups that covers this part. The reason being that the x2 internal group projects onto finite set x1. Okay. So there should be an internal one-dimensional definable subgroup of this group that contains this part. But then if it contains this part, it must contain everything that is generated by this part. Okay? And as we argued before, if I add this to itself, we get this point. If we add this part to itself, then you get this horizontal segment. And if you keep adding, you're going to get many horizontal segments, countably many, because of the choice of A being irrational. So this one-dimensional definable subgroup would contain a countable union of horizontal lines, and that's not possible because it would project on an infinite set on the x2 coordinate, and x1 inside sets of finite projection on x2. Okay, so one needs to play a little to see why with this changing of the lattice generator, you get a group which is not a product. Okay, so just was hoping to make a whole list of questions here. I'm not sure how far we get. Definable in. So this question one fails for this joint union. One fails. Now, as I said, the same argument, you can construct groups that are not products of one of xi internal groups in many of the other structures. So here, let me have the structure R with P, and P is going to be QRC or 2 to the Q. This is one sort of examples. Then could be density dependent set. Or 2 to the Z. Okay. Another example is I consider non-standard versions of this expansion. So here I have R P, which is a proper elementary extension of R bar to Z. Finally, I have semi-bounded pairs. So the same kind of example works in these settings, and here actually we get through in all the questions that I will manage to state. So let me just say, do whatever to say, because there is an independent theorem for this category only of mine that says that the G is actually defined isomorphic to an R-definable group. Okay. So we don't have new groups definable in R with an independent set. And now for this setting, R with 2 to the Z, actually I don't know the answer to question 1. Somehow I need to make a choice of that lattice generator A, and I can make it outside the standard copy of 2 to the Z, and the group I define works. But otherwise, I'm not sure. So this is open. Okay. Good. So now We found example, which is not product of xi internal groups, but still it's not that bad because it's a product of two xi internal sets. And if I take the product of this set, in this group, I generate the whole group, as one can check. So question 2 is G product of two xi subsets of G. Okay.
Internal subsets or subgroups or what?
Subsets.
Subsets. Oh,
Yes, subsets. So here, I could take any one of this set, take to this set. We can play with that multiplication and generate. So now that becomes a more likely to be true question. And question 2, this is true in the disjoint union in the case x1 and x2 are all minimal. So this is yes if xi is all minimal, and this is a theorem with Eleftheriou and Mamino, which is a preprint. Okay. But it's not known. No other cases. Here it is true, semi-bounded case, and this is an earlier work with Pantelis, where we analyzed the semi-bounded pairs. And really, the reason why I carry the semi-bounded category here is because the statements that we conjecture and prove for this case can be conjectured also in the other cases, the question mark cases. Because the structure theorem actually was, the decomposition was first proved for a semi-bounded case, and then we extended it to Payne pairs case. But I should say that this was worked with Philip and Ivan Nauden, but in this setting, but in other settings here is by Decomposing. All right. So for the rest 5 minutes, I would like to say what conjectures we hope to be true in the question marks. Okay. So a corollary of this in the disjoint union case is what we state in general as question 3 is G isomorphic to H1 cross H2 over a lattice where HI is now a definable group. Actually, it's a kind of union of definable sets. Restriction on each of those is definable, or the multiplication on each of those is definable. In Xi. So at the level of definable groups, we managed to find subgroups, somewhere groups, okay? And there is a lattice, by which I mean against a definable subgroup of this that intersects every finite subset of it at a finite set. Sorry, it intersects every definable subset of it at a finite set. Okay, so where is the first example? Yeah. So here I square would be H1 cross H2 And that square is the lattice. It happened to be definable as square, but in the non-standard setting, only definable. Okay, so now this follows from this theorem here because of orthogonality of the two, because it's disjoint union. So question 3 here is true. Okay. And the way you do it is you generate the subgroups of G from A1, from A2, and because of orthogonality, the intersection happens to be a lattice. So when you send now X comma Y to their product, the quotient happens to be a lattice. Okay? So you use orthogonality for that. In general, we don't know, even in the semi-bounded case. What we know in the semi-bounded case, and this is the main thing that I'm conjecturing, is the following question. Okay. The universal cover of G will not be as good as product of two definable groups, but it may be an extension, a group extension of such groups. So is G U over L, where L is a lattice, U is definable, and U as a group extension where H is both are being definable, but this is X R X1 internal. It's in fact generated by an X1 internal set. And K. So because we are not as symmetric as in the disjoint union case, we do hope to have something like this. And that was proved in the same bound case, same where. And it's of course true in the product case, in the disjoint union case. Good. The last thing I want to mention is question 5. Which there is enough thing to ask. All examples I know are subgroups of R definable groups. I don't know any other. Well, in the missing cases, to be honest. Here it will fail because we can have an X2 internal group, cannot be a subgroup of an X1 internal group. Here it fails for a similar reason, but for the rest, it's open. Only thing we know in this direction is a tiny theorem that I have that this is true for a group G definable in this case, but small. Okay. For small groups, it's true for G small group. Okay, so this is really analysis of groups definable in weakly or minimal non-vibrational structures, and there I've shown that such groups are subgroups, dense subgroups of groups definable in the orbital structure. Now, interestingly, these theorems could give some applications of group theoretic interest. So both this theorem in the same bounded case and this theorem for the small groups implies place conjecture or combat combination and combat combination conjecture in this case. Okay, it was not known for the same bounded case, and from this analysis we get it, and here it implied an extension of place conjecture in this weakly or minimal context. All right, so that's all I have to say. Thank you very much.
Yeah, so you said you're sort of looking into these questions for these contexts, but also other contexts where there's sort of this vague question makes sense. Are you familiar with the interpretive?
2 months. I've seen the work from not so much.
I feel like from everything that you've laid out, there's maybe not the whole interpolated fusion, because that includes like DCFA and DCF0 and random graphs, and maybe those aren't the right setting. But maybe there's, yeah, like a piece of the interpolated framework that exactly these methods are sort of fine for
Okay.
adaptation.
All set.
Questions? Thank you again.
Olivia?
Yes, thank you.
Very good. Thanks.